Hello, and welcome back to another lecture on methods in experimental ecology. Today we're going to get into generalized linear models. That's opposed to another term you might have heard. We've been calling linear models and analysis of variance, the kinds of things we've been doing so far this semester. Those used to be called general linear models. The generalized versions have moved beyond the 1970s era Pinto-style kinds of statistics to get really sophisticated into some high-tech, super-speed electronic vehicles like this competitor to Tesla that's coming out of Japan these days. So if we can liken the statistics we've been doing so far this semester to a 1970s era Pinto, it might be because we've found that we can get a lot more mileage, a lot more speed, a lot more good quality analyses out of these more advanced methods called generalized linear models. Now, you could also still argue that a good 1970s era Pinto can get you down the road and do a good job. It's perfectly suitable in some cases, and that's true. In fact, a linear model can still be perfectly appropriate, as can an analysis of variance. So I don't mean to reject those out of hand with my not so subtle joke here about the value of these vehicles. What I'm trying to say is that there's slicker, more sophisticated models out there now that help us get into more complicated kinds of data than a linear model or analysis of variance would have expected. So let's just revisit those briefly. What were those expectations? Well, for a linear model or an AOV, just to remind you, we are assuming that you have homogeneous variance and residuals, in other words, that were scattered evenly up and down the length of your regression and about evenly, left and right and up and down, and that we're having a normally distributed error term around your plot, right? Like the residuals would be centered around the zero line. For the generalized linear models, we have some options that allow for heterogeneous variance, which is great because what we've been trying to do is get data to match that assumption of homogeneous variance. Also, the generalized linear models allow us to play around with some different skew so you can have a non-normal distribution around your data. So, in other words, what we've been trying to do is make the data fit this fairly constrained set of assumptions for linear models and analysis of variance. Generalized linear models include some different assumptions. We can choose assumptions that better match the actual distributions in the data. So rather than forcing the data to match the model assumptions, we're allowing several different choices within generalized linear models to better match the data. Okay? So just as a reminder of what the graph would have had to look like for a linear model, ideally you would have seen a plot something like this with lots and lots of data points, where you'd get these nice bell curves up and down the whole length of the plot, and of course the bell curves are representing the assumption of normality throughout wherever we're going. But also we have this nice, fairly even-sized bell curves. The scatter fades out about symmetrically up and down all across, and that's the homogeneous variance that we hope to see in the residuals. And then, of course, there's those bell curves that are all nice and even and simply left-right, or in this case top-bottom, bell curves everywhere we go. Okay, that's what we would hope to have seen with linear models and analysis of variance. And when we had data, we tried to evaluate those kinds of patterns with plots like this. And in this one, it's not too bad. It's not as many data points, but it looks like the scatter left and right is about the same, up and down, pretty flat, as you might expect for homogeneous variance. And that's not bad. And it's also, looking with the local fit red line, looks like it's pretty centered on that zero line as well. And in addition, we can look at the normality plot, and we can see that it matches pretty closely to the assumptions for normality of error. So in this case, this data set was pretty decent. And again, we can find data sets like that. In this case, a linear model was perfectly appropriate. Well, we've also seen some data sets where that wasn't quite the case. Here's an extreme. If you had data that had residuals shaped like this and a normal curve that was shaped like that, you'd be pretty worried, as you should be, because clearly your data are not matching assumptions very well. Well, that's somewhat of an artificial data set that people built with a program to generate artificial data. What might some real data look like? Maybe something more like this, where we have these clumps of data, and in fact the whole trend looks like it's not fitting our even variance very well. There's a fairly tight bundle here north-south of the line, but there's a bit more scatter and a bit more pattern to it, and another set of pattern over here. So this would be a problem where we have these groups that themselves have some variation among them in their pattern above and below our line. And overall, there's maybe a problem with normality, especially at the upper end there, right? Or maybe we've seen data like this. This is actually turned sideways. For some reason, we've got the normality plot down here. But again, we see somewhat of a general curvature in the pattern. But you might also notice that there's a V shape to this general pattern, where it looks like we're getting greater and greater variance off to the right-hand side here relative to the left-hand side. So that would indicate we have a heterogeneity variance problem, and the normality is not looking very good either. So these are the data kinds of problems we've been messing around with, and that's where GLMs come in, where we can say it's okay if we have data that look like this. Let's use an assumption set that better matches that actual distribution. Okay, so there's ways that we can do that in a generalized linear model that depend on how we choose the family of the distribution inside the model statement, which we'll get around to in the second lecture. I'll show you some examples of how these work. Let's focus first on how these distributions work, because that's the key to a generalized linear model, where we're getting away from the simple normal data distribution. Now, you should notice the first one that comes up here in this list is the Gaussian, and I'll explain more about what this link means, but the Gaussian model is itself the normal distribution. So you should be thinking already that the generalized linear models allow us to do the standard linear model, because we would just choose the Gaussian family, and that's identical to doing a linear model, right? So let's use that Gaussian distribution to help think about what is this link function doing. A link is just simply talking about how you connect the average y to the linear predictor that you're using in your model. Because remember, this is a generalized linear model. We're still playing with linear models when I get into nonlinear functions. So this link function is what you already know for a Gaussian distribution, and the identity link is just saying the average y value is just what you get from your predicted model. It's not transforming it in any way. It's not using some other calculation. It's just your linear model, the predicted one. If I can go back up here, where's my nice pretty graph? Like this, the mean y across all of my scatter of all my points, the mean y value would be just simply the mean of my line that I would have predicted all along. Okay, so what we can bet then from the Gaussian models is that it's going to be identical to the linear model, and it's using this normal Gaussian distribution as a way to link our predicted model to the actual raw data as you see from the mean. Okay, so it's just simply the linear equation that we've been seeing all along. So this link function that we specify is just a way to connect the data to the linear predictor. It's the way we're describing how the function is connected to the data. Okay, so if we keep that basic definition in mind for a link, maybe we can move forward into some of the more fancy versions. So like this next one would be a log link, where we're taking the natural log of y would look better to the predicted y. So the natural log of our y values would match our predictions. Okay, so the prediction is another way to say that is the natural log of the y, if you want. So what we have here is this assumption that we have a skewy data set, and we would be just like log transforming in the past. It's a little bit different, but still the same principle. The log transform can adjust the data to make it look more normal. So if you're going to log transform data, those values have to be greater than 0, and that would match very nicely if we're dealing with things like counts. The other thing that happens if you're playing with either a Poisson or the negative binomial distributions is that they assume you have integer data. I counted 1, 2, 3, 4, etc. birds, not continuous data or real data. So for Poisson in negative binomial distributions, it really matches nicely with people who have count data. Okay. Now the way that a Poisson or a negative binomial distribution work is by just simply choosing or letting the computer solve for which lambda or r or whatever coefficient you want to call it is being used to adjust the shape of the distribution. At a lower lambda, it gets to be very skewed, and at a higher lambda, it becomes more normal. The same thing's being represented here with this R coefficient. You could call it another thing if you wanted to, lambda. Notice that as it gets larger, it increases up to more of a normal distribution. So it's the same principle as our log transformation, but it's handling it a little bit differently. And I'll explain why in just a second. The point is that if your original y data are really nicely homoscedastic around an exponential curve, then you should use this log link, because what you're doing essentially is that you're fitting the data well to a logarithmic curve. If, on the other hand, the data have a lot more variance as the mean gets bigger, one of those wedge-shaped distributions, you should use a log transform of the data, which helps change the shape of that distribution, but that's operating differently on how the data are being estimated in the models. So this is what I'm talking about if I say the data are homoscedastic around an exponential function. The data are pretty evenly distributed north and south of the line here. I know it's a little tighter down this way, but they're pretty evenly distributed around that line. That would be appropriate for using a log link because they really are represented well by this exponential function. Okay? If there's this kind of a wedge shape to an exponential function of some kind, logarithmic function, in this case curling in the opposite direction, what we have is a much greater variance at the right hand than we have at the left hand. Then that wedge-shaped pattern to the data, the original data, indicates that we should instead be doing this log transformation, as we've been playing around with in lab already. Now, the bit that I can understand in the rules and in the discussions that are out there on how to use R is that the decision on whether you should be using a generalized linear model with a log link or having log transformed your data first and then just doing a linear model is somewhat subjective, and the deciding point on how you should go really would depend on the residual plots. The residual plots would be your guide as to whether this was more appropriate or this wedge-shaped thing was more appropriate. Okay? So that's where those residual plots come in and help a lot. All right, let's move on to the next link. This one is called the inverse Gaussian link. I haven't seen this one used as much in ecology, but it looks like it might be somewhat useful, where it has this kind of a very skewy distribution again. It can peak quite highly over here and have quite a strong skew. Again, you can change the settings to be able to obtain more or less of that skew. The data have to be greater than 0 again, and it can maintain that peak then a bit above 0, so it's a very skewed, very log-normally kind of shape to the data, it seems to me. That's another way to play around with skewed distributions. And then finally, there's this other one called a gamma link, which is related to the Poisson and the binomials, because you're doing the same sort of thing. You're changing the tune of the distribution from being quite normal all the way up here to the upper end to very skewed, peaking essentially at 0. So this is even potentially more skewed than inverse Gaussian. I think this can be quite flexible. I've been exploring it myself. I'm wondering why not use this. One of the reasons that people haven't used it so much is apparently it's harder to diagnose as to how well your data really fit it, and therefore it's hard to say that that was the one to use, although it seems to be fairly commonly used because of its flexibility. The data have to be greater than 0, again, like a lot of these other things. So we have this increasing sequence, I would say, of how much skew you can expect to see in the data. The Gaussian one, again, remember, that's just like our linear models, assume this nice balanced normal distribution and homogeneous variance. And if we have problems with those assumptions and greater amounts of skew and therefore error on both sides of our residual plot being different, we can turn up the dial a bit and become more and more divergent from the normal distribution. And I think the gamma can allow us to be quite flexible around that case. Okay, so these would be the ones that allow us to play around with different amounts of skew. Another one is this binomial distribution, which I set apart because it's not about normal or quasi-semi-normal data that we can mess around with skew. It's really focused on binary kinds of data. And then there's another set of models we can use in the package GLM that can modify to some degree these ones just above, where we can bend the rules a bit on each of those other distributions. And I'll mention those briefly in just a second. But let's talk about this logit link, this binomial distribution. The logit link is really based on probabilities of success. So we're dealing with success or failure, P or Q, where Q is simply 1 minus P, as expressed here in this equation. So the probability of success relative to the probability of failure, or Q, and we just simply represent those two binary outcomes in a function by taking the natural logarithm of that. Now, that must be those data are greater than 0. They're counts, just like other data we've been playing around with, but they're really only counts of two kinds of outcomes, success or failure. So we're seeing these logistic-shaped models, and this is used in logistic regressions. It's used for Bernoulli and binomial and other kinds of data distributions, but logistic regressions, which we're going to spend some time on this semester, are based on these logit probabilities. Okay, so it yields this outcome called a log odds, which we'll spend some time on again later. It's related to probability, the natural log of these odds. So you can essentially use it to calculate the probabilities of success, for example, species surviving under a set of conditions, or failure, or let's say the number of hours required to obtain success on an exam, to pass an exam. Those kinds of data can be very common, actually, in a lot of ecological research where you have these binary outcomes, present or absent, etc., and you're trying to predict that with a number of other variables. So the logit function helps us work with those binary response variables in being able to obtain quantitative predictions, and can work quite well. Okay, then finally there is this quasi set of links, which are ways to handle over-dispersion. Now, over-dispersion was characterized by Crawley in his big book on R as just essentially a statistician's version of Murphy's Law. It's just saying that there are some other factors that we don't have data for that account for some more scatter in our response. There's more scatter than we would expect with the variables that we included in our model. There's something else going on. And so there are these approaches to modifying the distribution that we can change the Poisson or the binomial distributions that allow them a longer tail, essentially, to give ourselves some wiggle room to better fit the data, and using a distribution that you can prescribe in your statistical model. Remember, what we did in the past was that we were stuck with a normal Gaussian distribution, and we tried to reshape the data. Now what we simply say is we're going to modify the assumption for what we can work with in the generalized linear model and allow the data to stay in its original form. So the choice among these quasi-links is really important, and it should be based again on those residuals rather than just hunt and peck or arbitrary choices among them. I won't belabor those too much more because it gets a bit complicated to customize and choose among the quasi-links. But maybe this is a good way to summarize this. The GLM options have this, for the GLM package and the equations that we're going to be using, have this list of families that you specify in the model. Gaussian, Poisson, there's also a negative binomial which is available in some packages. It's closely related to the Poisson. The gamma distribution and the inverse Gaussian. The binomial, which is specific to using for logistic regressions. And then the quasi-distributions I was talking about. So for each of these things, there's this link function that you specify. The Gaussian, by definition, uses this identity link. The Poisson, the default is the log, but you can also specify other ones like square root. And so again, you can see sort of a relationship to how we've been doing transformations of data in the past. The gamma link assumes an inverse one, but you can also use the identity or log functions, which means that you can start coming up with some interesting combinations of some of these distributions. And the inverse Gaussian, again, you can play around with different choices. So actually, by choosing different link functions among these different families, you can come up with a nice combination of lots of data distributions to really make your model work as well as you should be able to get to, right? Let alone the possibilities of quasi. Now, this opens up a Pandora's box for ways to customize a GLM, but know that we can go way beyond this initial simple linear model AOV kind of approach. So when we did use certain versions of this, I'll leave this on the screen right here. You can read these as well as I can talk them. But I think the point is, when you have ideal kinds of data sets, we have homogeneous, normal residuals, real numbers, meaning continuous variable, with decimal places, etc. And that could be negative. You can use Gaussian. But notice that you have to have data that are greater than zeros for a lot of these other cases, or that are binary responses. So you can't necessarily always use all of these for all kinds of data, or you need to adjust all your data upwards so everything's greater than 0. Also notice that these are for integers, even though this one could be for real numbers, and so could this one. So there's limitations on which kinds of data you could use different kinds of families for, which is what's going to also then bound you. For example, for the Poisson, you have to have data that are greater than 0 in integers, but what if your data are real numbers and you want to analyze things? You can still do this, but it'll give you a warning that's not appropriate. So then you might be able to use, for example, the gamma with a log link, and then approaches that for a Poisson. You get the idea? So you can play around with these options and become far more flexible in how your model represents the data, okay? Rather than forcing the data to better fit the model. Okay, in the next lecture, I'm going to try to do some examples of how GLMs can work, and you'll have more chances to work with that sitting in front of the computer in lab as well. Talk to you next time.